Hello and welcome back for part 3 of our look at the urinary system, where we are beginning to actually look at the process of producing and making the urine. Um, and so we're going to go through that process. Right? Remember that this is really broken up into two main processes. Right? Process 1 is filtration, and process 2 is reabsorption and secretion. And the reason why I break these up into two different steps is because filtration is happening here within the renal corpuscle. Right? Whereas tubule reabsorption and tubule secretion is happening within the proximal, distal, and the loop of Henle. And so I'm dividing these processes up based off of location and where they are occurring. And so what we're going to be looking at here is, in this video here, is the process of filtration. And in the fourth video, our last video, we will go ahead and we will look at the processes of reabsorption and secretion. Once again, I just want to kind of draw your attention to some key terminology that you need to be aware of. Oh, this is going to not be good. Hold on, let's check. When we deal with the process of, oh yeah, no, I can't do that. Hold on, guys. When we deal with the process of filtration, what we are really dealing with here is we're dealing with the movement of fluid from the cardiovascular system into the capsular space. And so that is filtration. And what is produced? Production of filtrate. Now, that is very different than the processes of reabsorption and secretion. Right? Reabsorption is, again, the movement of fluid from the tubule into the capillaries. Secretion, again, is the movement of fluid. And by the way, when I say fluid, fluid, let me just define this real quick. Fluid here is the liquid component plus all soluble materials. All right, so fluid here is defined as both not only the liquid, not only the water aspect of it, but also everything that is dissolved within the water that is moving across the membranes. And so secretion, once again here, is the movement of fluid from the capillaries into the tubules. All right, and so that sets us up with a little bit of understanding as far as what we are really looking at here. And so this here is a really good diagram from the perspective of we see that we have reabsorption, we see that we have some secretion that is happening here. Within the loop of Henle, we are doing all reabsorption. And then again in the distal convoluted tubule, we are doing reabsorption and secretion, primarily secretion, less emphasis on the reabsorption. And then again in the collecting duct, we're again doing reabsorption and secretion. More of an emphasis here on reabsorption. Right, so more of a reabsorption in the proximal convoluted tubule on reabsorption, more of an emphasis on secretion within the distal, and more of an emphasis on reabsorption once again in the proximal, within the collecting duct. All right. So let's start our look at this process of filtration. So, filtration, again, movement of fluid and molecules from the capillaries of the glomerulus into the capsular space, as we already defined. But here's the trick to this. All right? The devil's always in the details, as we know. This movement of fluid, this movement of primarily water and the dissolved molecules, the dissolved components of that, isn't just moving from the capillaries, isn't just moving from the glomerulus into the capsular space. There's actually 3 layers that are separating the glomerulus from the capsular space. We have these things called fenestrated capillaries. We also have a basement membrane, and we have these things called filtration slits. And each of these, as we will discover here, have very different functions. What do I mean by that? Well, they tend to selectively exclude or allow things based off of very different criteria. All right, so fenestrated capillaries, right? Fenestrated capillaries, they tend to exclude things based off of size. So in other words, red blood cells and proteins tend to stay in the capillaries. They're too large to pass through these fenestrated capillaries. Basement membranes tend to selectively exclude or allow things to pass across the membrane based off of electrical charge. And so the membrane itself is negatively charged. All right. So again, things like albumin, which tend to be more negatively charged, negative ions or negative molecules repel one another. So albumin as a protein tends to not get past the basement membranes strictly because of the fact that it's negatively charged, and negatively charged molecules repel other negatively charged molecules. Now, that's not to say that if it was small enough that it still wouldn't pass through. Albumin's also a rather large molecule, so both of those things counter one another. And then your filtration slits, well, these are size-based, whether or not it excludes, and the filtration slits are basically regulated by your podocytes. And so we'll talk more about that here in a few moments. All right, so let's kind of go back and look at what these three layers look like. All right, so this is what you're all looking at right here. And so if we look here, I get tired of red for a laser pointer. Let's see. Let's do green. So if we look here, right, this here is your capillary. These are your red blood cells that are coming down here. Right. This here, this layer right here, this is your fenestrated or your fenestrated slits, right, or your fenestrated capillaries. And so you can see here you've got openings within the membrane of the capillaries that are going to allow almost everything to go through. Right? What it's excluding, once again, are red blood cells, white blood cells, plasma proteins, proteins, protein-bound minerals and hormones. Basically, anything that is larger than 8 nanometers in diameter is going to get blocked. Right? And so these fenestrated capillaries, this is not adjustable. Right? So this allows for a lot of things to go through, and it's excluding things that are rather large in nature. And then here you've got your basement membrane. Right? Once again, this basement membrane is negatively charged, and so this is also blocking based off of charge. Now, what's it allowing to go through? Well, it's allowing things like water, electrolytes, glucose, amino acids, fatty acids, vitamins, urea, uric acid, creatinine. All right? Urea, uric acid, and creatinine are all metabolic waste products. All right? Vitamins, fatty acids, amino acids, glucose, electrolytes, and water are all things that the body needs and most likely will end up reabsorbing later on. But because we're regulating plasma volume, all of these things are getting excluded from the plasma as water is moving because all of these things are dissolved within the water. So all of these things pass through as solvent drag is dragging that water or is dragging those molecules and those other materials dissolved within the water. And then you have your podocytes. These here are your filtration slits. And so the area between the podocytes is the filtration slit. So if these podocytes constrict, they contract, the filtration slits get bigger. It allows for more filtration. It allows for more fluid to be pulled from the plasma. If those podocytes are more relaxed, these filtration slits are smaller, and that's not allowing as much water and dissolved particles to leave the plasma. So in other words, when the filtration slit is smaller, the blood is retaining more fluid. Pressure remains higher in the capillary because not as much filtration is happening. But when those podocytes are contracted and the filtration slits are larger, then the pressure is being decreased within the capillaries, and that filtrate is flowing into the capsular space, which is right here, which is increasing the pressure within the capsular space. Some of you are probably wishing that I would write that down. I can hear you thinking it, and so because I can hear you thinking it, I will do it. Right? So, decreased filtration slits space leads to decreased filtrate production. It leads to retainment of more plasma volume, and it leads to stable or increased capillary pressure. Whereas increased filtration slit space will lead to increased filtrate production. It leads to decreased plasma volume. It leads to decreased capillary pressure. And it leads to an increased capsular space pressure. All right. Is that making sense? Whew. Okay. It's a lot to digest. So, how do we regulate whether or not we are increasing that pressure or decreasing that pressure? And what is normal? Well, to understand this, we have to go back and we have to visit some of the things that we talked about that occurs within capillary beds during the cardiovascular system. And so we've got to look at blood hydrostatic pressure, and we've got to look at colloid osmotic pressure, and we have to look at capsular pressure. These are the exact same three things that we looked at when we talked about filtering blood or reabsorption of waste products within capillary beds and the tissue. It's the same thing. We've just moved from capillary beds within the tissue to a specialized capillary bed known as the glomerulus, contained within the renal corpuscle. And so same scenario as what we talked about before, just a different location. Oops. And so what do we have going on in here? Well, blood hydrostatic pressure, that is the pressure within the glomerulus. Right? That is the pressure of the blood within the glomerulus. So how much pressure is just the plasma volume itself applying to the wall of the glomerulus? Right? Blood hydrostatic pressure equals the pressure of the plasma volume exerted on the wall of the glomerulus. All right. That pressure remains high, and this is a difference between what we talked about within the cardiovascular system and what we see within the urinary system, because blood hydrostatic pressure remains high throughout the capillary bed. We don't drop it. We don't decrease that pressure like we saw within the capillary beds. And here's why. You have a high rate of flow in through the afferent arteriole. The afferent arteriole has a wider diameter. You allow for more blood flow in. But look at the diameter of the efferent arteriole. It's constricted. So in other words, we allow for a higher rate of flow into the glomerulus but we back that blood flow out through the efferent by having a smaller diameter. And what that does is that maintains high pressure throughout the glomerulus. Traffic is flowing free and fast. And all of a sudden, you hit traffic and you slow down. And the amount of cars that can get through a particular area is reduced. Blood is flowing fast and free. It comes through the glomerulus, and the blood begins to back up because the efferent is constricted. And so you maintain high pressure throughout the glomerulus, approximately 60 millimeters of pressure forcing outward. But you also have colloid osmotic pressure, the amount of pressure applied by the proteins and the large solutes that are in the plasma that cannot pass the fenestrated capillaries, that cannot pass the basement membrane, that cannot pass the filtration slits. And so that colloid osmotic pressure is both the proteins, I should say it is the proteins and the solutes in the blood. Remember, that's creating its own pressure. 32 millimeters of mercury fighting against the 60 millimeters of mercury forcing outward. And you have capsular pressure. In other words, as this capsular space fills with filtrate, it applies pressure onto the glomerulus. The more the capsular space fills, the more pressure is exerted on the glomerulus, the less filtering is going to occur. And so your net filtration rate, or your net filtration pressure, your NFP, is 10 millimeters of mercury out. And that is maintained throughout the glomerulus. Blood hydrostatic pressure remains higher throughout the system. And the whole premise of this is you want to conduct filtration through the entire glomerulus. If blood hydrostatic pressure was allowed to drop, what would begin to happen inside of the capsular space? You'd start reabsorption. You would start reabsorbing everything that you just got rid of. You don't want that to happen. You want to block, you want to prevent, you want to inhibit reabsorption in the renal corpuscle. And so you have to maintain higher blood hydrostatic pressure through the glomerulus. And in doing so, you maintain filtration throughout. This is a video. I'm not going to play the video now, but you've got this slide here, and that will review for you glomerular filtration. The rate of filtration is equal to net filtration pressure is equal to about 12.5 milliliters of filtrate per minute. And so that is what we are maintaining within the renal corpuscle. We are maintaining this rate of producing about 12.5 milliliters of filtrate per minute, right, by keeping that osmotic pressure and the blood hydrostatic pressure where it is. So, all right, regulation, right? how do we regulate and maintain that high rate of flow in and that low rate of flow out? Well, this is where the juxtaglomerular apparatus comes into play. So there is something referred to as tubular glomerular feedback. In other words, tubular glomerular. The tubular part is the capillaries. Right? The capillaries that is flowing through the glomerulus. That pressure is being constantly monitored. And it's being monitored in the afferent arteriole and the efferent arteriole through what we refer to as the juxtaglomerular apparatus. And so it's regulating and sensing and monitoring changes in pressure and fluid composition. Right? And it's doing that, again, primarily on the afferent, but also to some degree on the efferent. And so what you're seeing right here is that scenario of the juxtaglomerular apparatus. So here's the afferent arteriole coming into the glomerulus. Here's the efferent arteriole heading out. Right? Here are those JG cells on the afferent arteriole. There are also JG cells on the efferent arteriole. And these JG cells are monitoring pressure. They're monitoring primarily pressure. All right. If there is higher pressure coming into the afferent arteriole, that means you have higher plasma volume. And so you are going to increase the rate of filtration in the glomerulus. How do you do that? Well, you vasodilate on the afferent, you vasoconstrict on the efferent. What does that do? That slows the rate at which the blood is flowing through the glomerulus and allows for more filtration. More filtrate equals reduced blood volume and plasma volume, which decreases blood pressure. If your blood pressure is low, your JG cells will detect that. And when they detect that drop in pressure, the afferent will constrict, vasoconstrict. The efferent can actually vasodilate a little bit, and that allows for the blood to flow quicker. Less filtrate is produced. Less filtrate is produced. A lot of this is regulated through the sympathetic nervous system. All right. And so during exercise, your sympathetic nervous system is kicked up, which means you want to go ahead and decrease the rate at which you are producing filtrate, because you don't want to have to stop and have to use the bathroom. And so you constrict the afferent arteriole, which diverts the blood back into the cardiovascular system to support the muscular tissue and the nervous tissue and other tissues, skeletal muscle tissue, that you're going to need in order to support whatever that sympathetic activity is. And so, for example, during exercise, you constrict the afferent arterioles. This reduces the glomerular filtration rate, which reduces urine production. And so that way, you're supporting sympathetic activity. Right? During parasympathetic activity, the opposite would happen. Right? You're going to go ahead and vasodilate that afferent, which is going to increase glomerular filtration rate, which is going to increase the rate of production of the filtrate. So that way you can, again, regulate plasma level, blood pressure, blood composition, pH, balance. We're going to find out is also regulated through here. And this is where we end, and this is where we come into, and we're almost done here. We're almost done here. this is where we come into our RAS mechanism, our renin-angiotensin aldosterone system. And so let's kind of look at this here. All right, I'll try to make this as painless as I can. Follow my little schematic that I have over here, and nobody will get hurt, I promise. And so what ends up happening here is we start the process right here with the kidney. All right, now in this scenario, we're going to start with the assumption that there is a drop in blood pressure. All right, so blood pressure is detected as dropping in those JG cells, and the JG cells is going to go ahead and secrete renin. All right. Renin is then going to mix, if you would, with an enzyme that is being secreted from the liver. Now, the liver is always producing angiotensinogen. Right? The liver is always producing through, is always producing angiotensinogen. The difference is angiotensinogen is inactive in its initial form. It is not activated until renin is released. So renin cleaves, or renin shortens angiotensinogen. Right? It's what's going to allow it to be active. Well, renin's not always available. Why? Because blood pressure is usually stabilized. Right? But if we detect in the JG cells, in the juxtaglomerular cells, a drop in pressure coming through the afferent arteriole, those JG cells are going to secrete renin, which is going to cleave angiotensinogen, and that creates angiotensin 1. Angiotensin 1 is then going to be cleaved by another enzyme called angiotensin converting enzyme, ACE. And that is produced in the lungs. Now let's think about this. The lungs play a critical role in maintaining blood pressure. Yes, we can agree to that. Yes, hopefully. All right. So if you have higher cardiac output, you have more blood being delivered to the lungs, your lungs are functioning at a higher rate. Right? So if your lungs are detecting an increase in blood pressure, everything's good. But if the cardiac output decreases, the rate of flow to the lungs decreases, the lungs start to say, crap, I've got decreased blood flow coming to me, blood pressure's dropping. And so the lungs detect the drop in blood pressure, and they secrete ACE. They secrete the angiotensin converting enzyme, which cleaves angiotensin 1. Notice this is a scenario of backup. All right. So just the lungs detecting a drop in blood pressure isn't enough. Both the lungs and the kidneys have to detect this change in blood pressure. They have to detect this drop in blood pressure, because just releasing ACE isn't going to do anything to angiotensinogen. Renin is going to act on angiotensinogen, creating angiotensin 1. ACE is going to only act on angiotensin 1, creating angiotensin 2. And what does angiotensin 2 do in order to increase blood pressure? Well, it's going to cause vasoconstriction within the arterioles. Angiotensin 2 is going to tell the hypothalamus to initiate the thirst complex. It's going to make you drink, hopefully water, because that water is going to quickly be absorbed in the duodenum and in the jejunum into the cardiovascular system to increase blood plasma levels, to increase that blood pressure. And angiotensin 2 is going to communicate with the adrenal gland within the zona glomerulosa, the zona glomerulosus, notice the connection there, to secrete aldosterone, and aldosterone is going to act on the distal convoluted tubule to increase water reabsorption from the filtrate. We actually increase salt reabsorption. Now, the other thing that will happen here is angiotensinogen 2 will block the release of antidiuretic. I'm sorry, it will initiate the release of antidiuretic hormone. So angiotensin 2 also stimulates the pituitary gland to secrete ADH, which is going to reabsorb even more water. And it's going to do that through the distal convoluted tubule. Aldosterone is going to act primarily on the loop of Henle to reabsorb salt, which is going to force the reabsorption of more water. Angiotensin 2 is going to act on the pituitary gland to secrete ADH, which is going to act on the distal convoluted tubule to go ahead and reabsorb more water. It's going to act on the hypothalamus to initiate thirst, so you're drinking more, and it's going to cause vasoconstriction. All of this to raise the blood pressure back up. I know I've said this before. This is why when you drink excessive amounts of alcohol, alcohol inhibits ADH, which means it promotes higher water release. You urinate more, which dehydrates you, which causes the headache and the hangover. But that's RAS. That's the renin-angiotensin-aldosterone system. Right. JG cells detect a drop in blood pressure, releases renin, which goes ahead and cleaves angiotensinogen produced by the liver, which is always being produced by the liver. Cleaves into angiotensin 1, which is then cleaved by ACE, released by the lungs, because the lungs have detected a drop in blood pressure, creating angiotensin 2. Angiotensin 2 is the active form that is going to initiate the emergency response to increase blood pressure by initiating the thirst response, drinking water to increase plasma levels. It's going to cause vasoconstriction to go ahead and create more resistance in the arterioles to increase blood pressure. It's going to initiate the release of aldosterone for salt retention to go ahead and absorb more water along the loop of Henle, and it's going to stimulate the pituitary gland to secrete ADH, antidiuretic hormone, which is going to act on the distal convoluted tubules to reabsorb even more water. Holy poop! That's a lot! Make sure you understand that. I like to put this on the exam. Now, there is a video there that is going to really, kind of summarize that for you. Pay attention to it, please. And here is a nice little summary table of everything that is happening when we talk about glomerular filtration regulation and the production of filtrate. And I have kept you for 40 minutes. This is a little bit longer of a video, but there is a lot to go over when we talk about filtration. And so I'm going to give you some time to digest this, to analyze this, to answer some questions, and to ask questions. And with that, I shall see you on the flip side.